Welcome, deep divers. You know, in the AI world, things move so fast, it's almost dizzying. Like every week there's something new, something powerful.
Mm,
Keeping up is tough, right?
okay.
So that's what we're here for. Today we're doing a deep dive into something really cool, maybe a bit under the radar, but potentially game-changing for AI learning. We've all seen what large language models can do. GPT-3, PaLM, you name it. They have this amazing trick called in-context learning.
Yeah,
You just show them a few examples, give a quick prompt, and bam, they adapt. Almost like magic. No big retraining needed, feels super intuitive. But there's a catch, a kind of core tension here. While they're incredibly powerful, there's something about their design.
exactly. Standard transformers, yeah, they're huge. They can fit data like crazy in context, but they fundamentally lack an iterative structure. Think about classic machine learning. Lots of algorithms work step by step, right? Refining the answer, like gradient descent. Standard transformers, though, they're usually feed forward. Fixed layers are not really built to naturally mimic that gradual refinement. They often try to get the whole answer in one big go.
Right. And that makes you think, doesn't it? Like, what if you could bridge that gap? What if these powerful models could learn to think more algorithmically, step by step? I bet the researchers behind this, wrestling with it, must have had these moments, like an internal monologue. Maybe something like this. Okay, you train standard transformers on in-context learning. They solve data-fitting tasks. Sure, fine. But they lack something, that iterative structure. Can't mimic gradient descent's step-by-step flow. So, you design a looped architecture. Right. Feed inputs back, share the layer weights, train it, make it iterate, converge, improve. Okay, test it. Linear regression. Oh, wow. It matches the standard transformer's performance. But wait, with 112 of the parameters, you stare at the numbers 0.79 AMA versus 9.4 AMA. Hold on, you realize it's not just smaller, it's actually smarter about how it computes. Okay, push it. Sparse linear functions. Whoa, it outperforms Lasso. Outperforms the unlooped model. With fewer examples, it gets the pattern. Okay? Check decision trees. Two-layer re-LUs. Same story matches or beats the standard one. Huh. You probe its layers. Well, it's loops. It doesn't just jump to the answer. It refines step by step, like an algorithm should. Okay, you realize it's learning the process, not just the final answer. All right, train it on fewer distinct prompts. It learns faster. Needs less data. Okay, interesting. Test out of distribution. Skewed covariance. Handles it better. Noisy inputs. Reduced double descent. Nice. You tweak the loops. B, the window. T, find that sweet spot where it stabilizes and look beyond the trained steps it keeps converging. A fixed point, not a collapse. Okay. Run it on OpenML data sets, real-world stuff, not just synthetic tasks. Holds its own, sometimes better. You step back. This isn't just a smaller transformer. It's a learner that learns how to learn. With loops, not just layers stacked high, it emulates the iterative heart of ML. You realize, you didn't just build a better model for linear regression, you built a bridge between transformers and algorithms. Smaller, sparser, but deeper. A loop that loops toward what learning actually is. Okay, let's unpack that. Today, yeah, we're diving deep into looped transformers. This is groundbreaking stuff from researchers Liu Yang, Kangwook Lee, Robert Nowak, and Dimitris Papailiopoulos at UW-Madison. It's an architecture trying to bridge that gap we mentioned between those huge, sometimes opaque AI models and the efficient step-by-step thinking of classic algorithms.
And the so what for you listening is really significant. This isn't just some academic tweak. It's about making powerful AI potentially much more accessible, more sustainable, lower resource needs. And it changes how we think about what these models are doing. Are they just pattern matching or are they actually learning a process? It points towards AI that might be more efficient, maybe more understandable, and perhaps more genuinely intelligent in how it learns.
The iterative problem of standard transformers.
Right, so let's nail down this core challenge first. As we kind of touched on, lots of basic ML problems, think linear regression, they're solved iteratively. The algorithms just keep refining the answer step by step until they get it right.
That's a really key point. Take linear regression, finding the best line through data points. There's a direct math solution, OLS, ordinary least squares. But it involves a tricky matrix inverse calculation. In practice, methods like gradient descent are often used. It's simpler, computationally just repeated matrix multiplications, tweaking the line bit by bit. The problem is standard transformers with their fixed feed-forward structure, they aren't naturally set up for that. They tend to try and compute something more like that complex OLS solution in one pass.
Which can be, well, less efficient or maybe less stable than just iterating towards the answer.
Potentially, yeah. Especially as problems get more complex, there's this inherent mismatch between the architecture and the iterative nature of many optimal algorithms.
So that's the gap. Standard transformers are powerful pattern matchers, but they don't inherently think iteratively like many algorithms do.
The loop transformer, An iterative revolution.
Okay, so this is where it gets super interesting. The solution proposed by these researchers, the looped transformer.
It's a really clever architectural shift. Instead of stacking, say, 12 different layers, each with its own unique set of weights, a looped transformer basically reuses the same set of weights, maybe just one effective layer's worth, over and over again in loop iterations.
Ah, like an RNN or LSTM kind of idea, but applied within the transformer structure.
Exactly, that's a good analogy. It shares weights across time, or in this case, across computational steps or loops. Think of it like one really good chef constantly tasting and adjusting the soup, instead of 12 different chefs just adding one ingredient each. And this weight sharing, that's the key to the massive parameter savings. It's hugely efficient.
How efficient are we talking?
Well, in their experiments, a loop model, often with just that one effective layer looped many times, got similar results to a standard 12-layer transformer.
Yeah.
But using less than 10% of the parameters, they cite numbers like 0.79 million parameters for the looped one versus 9.48 million for the standard one.
Wow, okay. That's a massive difference. Smaller models, faster training, less memory needed.
Precisely. It really lowers the barrier to using these powerful models.
But okay, how do you actually train something that learns by looping? It sounds like it could easily just go off the rails.
Right, you need stability.
Oh.
And a key technique they use is called input injection.
Hmm.
The original input prompt isn't just fed in at the start, it gets repeatedly added back in or combined with the output from the previous loops.
Why is that so important?
Because without it, the memory of the initial task, the original input, it would just fade away as you loop more and more. The model would forget what it was supposed to be doing. You'd end up with random or unpredictable behavior, divergence. It's a known issue in other kinds of weight-time models if you don't keep injecting that core information.
Makes sense. Keep reminding it of the goal. Are there other key training details?
Yeah, two important parameters. B and TB is the maximum number of loops it does during training. Think of it as how many refinement steps you let the chef practice. A higher B helps the model learn to find a stable endpoint, a fixed point solution, so it doesn't diverge later when you let it run longer during inference.
And T.
T is the truncated loss window. You only calculate the error and backpropagate through the last T loops. This is mainly a practical trick to save memory and compute during training. You don't need to backprop through, say, 50 loops if T is 15.
Ah, okay. So there's a trade-off then. More loops, B, might mean better convergence, but longer training and inference. And a bigger window, T, might help performance, but cost more memory or cause instability.
Exactly. You have to find a sweet spot. For linear regression, they found something like B20 and T15 worked well. Interestingly, they also found that sometimes gradually increasing B during training, sort of like giving it a kickstart, could lead to even better results, especially for harder tasks like decision trees.
The proof is in the pudding looped transformer's performance.
Okay, the theory, the training tricks, it all sounds very neat, but does it actually work? What do the results show? Does this looped transformer deliver?
Oh, absolutely. The results are pretty striking. Like we heard in that Imagine monologue, for basic linear regression, that looped model with way fewer parameters, 0.79 million versus 9.48 million, it didn't just match the standard transformer's performance. It also got results very close to the traditional optimal OLS solver. And crucially, it learned to find that stable fixed point solution.
Meaning it keeps getting the right answer even if you let it loop more times than it saw during training.
Exactly. It suggests it's not just memorizing a fixed computation path, but learning something more like the actual iterative process of solving the problem. True algorithmic behavior.
And that efficiency carries over to data needs, too.
Yes, definitely. Because it has fewer parameters to tune, it's much more sample efficient. It needs fewer different examples, fewer distinct prompts or functions during training to learn a task effectively compared to the bigger standard models. Less data, faster learning.
Okay, linear regression is one thing. What about harder problems?
This is where it gets really interesting. For sparse linear regression, where the answer depends only on a few inputs, the loop transformer was a clear winner. It significantly outperformed the standard transformer and even beat Lasso, which is a standard algorithm specifically designed for sparsity, especially when you only give it a few examples.
Why would it be better at sparse problems?
It seems to have an inherent inductive bias towards simpler solutions. Because it's reusing the same weights, it naturally favors solutions that don't require incredibly complex, unique computations at each step. Sparsity is a form of simplicity.
Makes sense. And other complex tasks, like decision trees or simple neural nets?
For those, like decision trees and two-layer ReLU networks, the looped transformer consistently matched the performance of the standard transformer. So it holds its own even on more complex function classes, despite its parameter efficiency.
And this simplicity bias, how does that affect how it handles weird data it hasn't seen before, out of distribution data?
That bias seems to help in some cases. It showed better performance on tasks with skewed input data, covariance shift, and on noisy linear regression. It actually reduced the error peaks you sometimes see in double descent, which is kind of similar to what regularization techniques do. They also often encourage simpler solutions.
But is there a downside to that simplicity bias?
Potentially, yes. They noted it could sometimes hurt performance if the input data during testing had drastically different scales compared to the training data. So it's not universally better Odo, but it shows interesting robustness properties.
So performance is great, efficiency is great, but how do they confirm it's actually learning differently? That internal process, you mentioned model probing.
Right. They looked inside the models during computation. They found that standard transformers might identify important features, like gradient components early on, but then later layers might shift focus to other things. The looped transformer, however, showed a different pattern. Across each loop iteration, it consistently refined its internal representations related to the target solution.
So it's really iterating, refining its thought process step by step towards the answer.
That's what the probing suggests, yeah. It reinforces this idea that it's learning the process, the algorithm, not just pattern matching to a final answer.
And this wasn't just on made-up problems.
Nope. They validated it on 10 real-world data sets from the OpenML benchmark, and the results held up comparable and sometimes even better performance than standard transformers. It shows this isn't just a theoretical curiosity, it has practical legs.
The bigger picture and future horizons.
Okay, pulling back a bit. What's the big picture here? What does this looped transformer concept mean for where AI is heading?
I think it's genuinely significant. It really does build a kind of bridge between transformers and algorithms. You get the representational power of transformers, their ability to learn from complex data, but you combine it with the iterative, often more robust and understandable nature of classical algorithms. It's potentially the best of both worlds.
And you mentioned those parameters, B and T. They're not just knobs to tune, right?
Exactly. The optimal values seem to tell you something interesting, to sort of reflect the complexity of a task from the transformer's perspective. A harder task, maybe like learning a complex decision tree, might naturally require more iterations, B to converge reliably. It gives us this novel way to gauge how difficult a task is for the model itself.
Fascinating. But it's not perfect yet, right? What are the limitations or the next steps?
Right. While it's great at learning these fixed-point solutions within the kind of data it was trained on, it doesn't quite capture a general algorithm that works perfectly on any input distribution the way, say, standard gradient descent does theoretically. Improving that broad out-of-distribution generalization is a big area for future research, making it truly robust, like a traditional algorithm, but with the learning power of a transformer.
And maybe making the looping more dynamic.
Yeah, exactly. Things like adaptive looping. Could the model learn to adjust B or T on the fly, depending on the specific input or task? That could optimize things even further. Exploring those memory versus computation trade-offs is key.
So this whole concept of looped transformers, it feels like a really profound step. It's pushing towards AI that's not just powerful, but smarter in how it uses resources, more efficient, maybe more interpretable, and maybe more genuinely learning in a way we intuitively understand step-by-step refinement. Imagine smaller models doing just as much, maybe more, needing less data, less energy.
It really shifts the focus, doesn't it? From models that just compute an output based on patterns to models that seem to understand and perform a computational process. Iterative thinking. That could unlock ways to tackle problems that are currently too complex or resource-intensive. It opens up exciting new avenues for AI that's not just powerful, but also robust and maybe even transparent.
So it leaves you wondering, doesn't it, what other complex processes, maybe even outside of typical ML, could be unrolled and learned more efficiently just by adding a loop? What problem in your world might benefit from that kind of iterative, refining approach? That's the kind of thinking this work sparks. We hope you keep diving into these fascinating questions. Thanks for joining us for another deep dive.